the billion-dollar hue. The hunt for the perfect red pigment for centuries, artists and manufacturers have sought the holy grail of color. A vivid, long-lasting red pigment that is both brilliant and stable. Despite advances in chemistry, this elusive shade remains out of reach, representing a potential fortune for anyone who can synthesize it. The global inorganic pigment market is already worth over $28 billion annually, and the demand for a breakthrough red is intense. The historical struggle for vibrant reds, the earliest reds, were derived from iron oxide-containing rocks, creating earthy tones that have endured for millennia, as evidenced by 20,000-year-old cave paintings in France. However, historically, truly striking reds relied on toxic metals like cadmium and mercury. As these materials become increasingly restricted due to safety concerns, finding a replacement has proven far more challenging than anticipated. Organic pigments can produce brilliant reds, but their chemical fragility means they fade quickly. A modern Ferrari's iconic red requires a costly UV coating to prevent color loss. The accidental discovery of why in MN blue chemist Maz Subramanian stumbled upon a groundbreaking blue pigment in 2008 while researching materials for computers at Oregon State University. The discovery of why in MN blue, a combination of yttrium, indium, and manganese, was accidental, born from unconventional experimentation rather than deliberate design. His initial funding proposal hadn't even mentioned pigment discovery. It was a lucky byproduct of materials science research. The pigment quickly gained recognition for its stability and unique hue, finding use in paints, coatings for cooling buildings, and even artistic applications. However, the rare elements required to synthesize it make mass production expensive. The science behind color, broken symmetry, and atomic structure. Subramanian's work shifted his focus to the complexities of color at the atomic level. He discovered that color depends on how light interacts with electrons within materials. A material appears red because it reflects red light while absorbing others. But the most striking pigments reflect only the desired color without spectral leakage. This depends on how atoms are arranged, with highly symmetrical structures often suppressing the electron transitions needed for vibrant hues. To achieve vivid colors, Subramanian began exploiting asymmetry, deliberately breaking symmetry to allow electrons to jump between energy levels in ways that would normally be forbidden by quantum physics. He has experimented with chromium in unusual structures, inspired by lunar rock samples containing rare Cr2+ formations, which exhibit reddish magenta shades. The future of red, a race against chemistry despite progress, a true, stable, and affordable red remains elusive. The challenge lies in engineering asymmetry into pigments while ensuring durability against humidity, sunlight, and large-scale manufacturing. Subramanian continues to refine his approach, combining unconventional atomic arrangements with semiconductor materials to push the boundaries of color chemistry. The hunt for the perfect red is not just a scientific pursuit, it is a race for a potential billion-dollar payoff. The chemist's approach remains sound, but luck and serendipity may still play a role in unlocking the final breakthrough.